going, if you all go along with it. Okay, so everything I'm saying now will be recorded, and this will be in Blackboard. Now, the first one is on Blackboard. I don't know if you took a look at it or not, but I have a link to the Zoom lectures right below the link to how you get into this class. And so you could go look at that link. And right now I should tell you, because I'm trying to simplify the problem for some people we delegated this to. We have a couple of people in the department whose part of whose job is to take the videos that they find, that those of we make them, they will take them and transfer them over to YouTube. I don't do that. What happens, I put them someplace, they pick them up, sort of like a delivery service, and then they come back to me in Blackboard. So there's a delay on that because there's lots of people doing this. But hopefully, so far it's been within 24 hours or the same evening so far. So the Monday session actually was taped, and you can see it if you want to. I don't think it's worth much, but you can see it through that link. Did anybody look at the link? Anybody see that yet? Were you able to see it? There have been some Blackboard problems, I understand. There also have been some WebAssign problems. These places are getting overwhelmed. And so if you have trouble, please let me know about these things, because it may not be you. Sometimes you sit there for an hour worrying about how you're going to solve something that you think is your problem, and it turns out that the network's down and it wasn't your problem at all. So if you have difficulties, let me know. Anyway, the screen right now is showing some letters that we basically use and two quantifiers that I'm going to use. Instead of spelling out words like for every and for each and so forth, I may use these quantifiers. We'll get into how you use them and how they show up and so on later. And we started talking about this yesterday, so I'm not going to reiterate unless you guys want to interrupt me and ask questions, and I encourage you to do so. I assume that you are hearing me right now, and so you know that you can do that. Anyway, a relation is a set of ordered pairs, and that's a simple idea. And we're not thinking of ordered pairs in the plane necessarily. We're just thinking about two numbers when you say ordered pairs. When you put together a collection of ordered pairs, a set of ordered pairs, we get a relation. All functions are relations, but they're special relations. Namely, for a function, when you have two ordered pairs, they cannot have the same first element unless they have the same second element. And so what you hear in elementary school or high school or wherever you first heard about functions is you didn't have any vertical lines cross the graph more than once. And a vertical line is where you have the same x value but different y values. Well, if you have pairs like that in your relation, that's okay. But if it's a function, you're not allowed to have that. So if you take a parabola and put it on its side, like x equals y squared instead of y equals x squared, that's not a function of x. It's a relation, but it's not a function. And that's because if you look at the idea of x equals y squared, that actually looks like a C. With you take your left hand and make a C with your thumb and forefinger, that's what the parabola looks like. That's not a function. Well, if you think about it, you have x values there with the same x value but different y values, and that's not allowed. Okay, so I know you know all that, but you need to kind of review that kind of stuff some. Also, I use the word source sometimes, because sometimes we say, in this class, we're going to say a real valued function of a complex variable, or a vector valued function of a real variable. And we use names like that. When I say of a real variable, I mean that the source, the x's that we're going to use are going to be real. If I say a complex valued function of a vector variable, then the domain is going to be vectors. If I say a vector valued function, then the range is going to be vectors. Okay, so I use source to tell you in general terms what we are talking about, the domain and target for what you end up with, except what you actually end up with is called the range. So the range is a subset of the target. It's all the second elements of this ordered pairs. the domain is a subset of the source, it's all the first things in the ordered pairs. Now, it's customary in textbooks. I'm sorry for my voice. I'm still taking some medicine to dry up the poison ivy, and it affects my voice because it dries up all my body, I guess. So I hear myself and I think how horrible I must sound to you guys. Because I do a lot of correcting my throat. Anyway, a lot of times in books, you'll see a formula and you won't be told what the domain or range is, and you have to sometimes work that out. Like the square root function, you can't have negative numbers if we're talking about real numbers, okay? You can have negative square roots if you talk, or square roots have negative things if you're talking about complex numbers and stuff, but we'll get to that sort of stuff later. Anyway, what I wanted to point out here is this equivalence relation idea, because we use equivalence relations all kinds of places that we haven't told you about. And the relevant place right now for equivalence relations in this class is with vectors. And so I'm going to give you, this is further on in the notes, but I'm just going to talk about it a little bit here. And some of you have heard all this already if you had the class from me before. But the textbook likes to call a directed line segment. So you take in the plane or in 3 dimensions, you take 2 points and you connect them and you make an arrow. As soon as you make an arrow between the 2 points, there's a head and there's a tail. And that's called a directed line segment. If you're just talking about all the points in between, that's called a non-directed line segment. It's just a line segment. We have open line segments if you do not include the endpoints. We have closed line segments if you include the endpoints. We can have half open and half closed and so forth, depending on which endpoint you include, okay, or not. We usually use the word between to mean open, to mean not the endpoints, but you have to be careful about that because some people use between to include the endpoints. And nobody, has anybody else come in? No, I have 20 of you now.
In your definition 5.
I think we'll take a snapshot and get that out of the way here. So let me do that. So, okay, here. Hopefully I can get these sort of things done quickly. So this thing says take the screenshot. Just a moment. To take the screenshot, click outside this window. No, okay. It's not doing it. Let me see here. No, it's not cooperating yet. Just a second. I evidently, sorry, okay, I evidently took a picture of the whole screen. That's fine. That includes you guys. So I'll get rid of that now. Okay, so going back to this, so we just get that out of the way. And we'll get more smooth about that later, I hope.
Dr. Brady?
Yes, sir.
In your definition 5, is that saying R is a proper subset or R is just a subset? Because I know we talked about that last semester.
Let's see here. If it is that's subset, not proper subset. In
Okay,
these notes, if a proper subset won't have the line underneath. So it could be all of these, if that's what you mean. To say R is a subset means it could be all. If I say A is a proper subset, then it means it's not everything. Does that answer your question?
Yes, thank you.
Okay.
And then that's referring to the Cartesian product, I suppose?
The Cartesian, yeah. The S cross S there, that XSS, that means the ordered pairs where you take something out of the first thing and something out of the second thing, okay? Now, in this particular case, I'm going to take 3 things. Each of these things, for an equivalence relation, and maybe I didn't write this, I sometimes think I made mistakes here. Anyway, I'm taking 3 things out of the set, and I'm going to use them in the following way. And when I compare the thing with itself, that has to be true for all things in R, all right? And that's called reflexive. If I take two things in the set and I pair them with X and Y, if they're paired and they're in the set, then when I turn them around, they have to be in the set. Okay, and one of the easiest things to do is to use it, like to say something like sit next to or something. And the question is, do you sit next to yourself? Well, only if you're schizophrenic, probably. And so that wouldn't be reflexive. But if I'm sitting next to you, you are sitting next to me automatically. And so that is symmetric. And you look at pairing up stuff, and it could be children, it could be parents, it could be weighing more than. If I weigh more than you, do you weigh more than me? And the answer is no, because it's not symmetric. But if I weigh more than you and you weigh more than the third person, then I weigh more than the third person. That's the third one there. That's called transitivity. Okay? And so the R is a bunch of pairs, and we take things from S. In this case, I needed 3 letters because I have the third one needs 3 letters here. So I take 3 things out of S, and I look over here and I say, okay, if I pair a thing with itself, is that always in the set? The set's a bunch of pairs because it's a subset of the pairs. Now, do I need to say any more about that, or is that kind of getting clearer?
I think that's getting clearer, yeah.
Okay, and this stuff, you have to study this stuff. And it's really, I try to carefully do it, but sometimes I'll also make grammatical or symbol mistakes, and then it'll screw you up. So you got to be looking at it, and if it doesn't make any sense, you got to ask me. Now, we're not going to use this very much. This is going to be the underlying theory for what we're talking about. So let me talk about vectors a second. And then it follows this thing right here. But I don't like to call vectors line segments any more than I like to call the pair 1, 2, let's say 1/2. The pair 1, 2 are the two numbers that make up a half, but a half is a lot more than just the numbers 1 and 2. A half is also 2 and 4 and 3 and 6 and 4 and 8 and -5 and -10 paired together. In other words, a half is actually a whole class of pairs of numbers. And when you take two numbers and put them together with one over the other, you make a fraction, but you have a lot of choices of the same fraction. So the point is that we have a relationship between integers that pairs integers up so that the equivalence classes, the classes you get, the pairs that are related turn out to be the fractions. Turn out to be 1, 2, 3, 4, not 3, 4, 1, 2, and 3, 4 would be in different classes. And vectors are the same way. What we want to do with a vector is make it sort of an object that you take representatives of. So if I want to draw a directed line segment in one place on the plane, and you want to draw it in a different place on the plane, the question is, when are we drawing the same vector? Well, we're not drawing the same vector because they're two different places on the screen if we say a vector is a directed line segment, because two line segments are different. They have different numbers in them. But if we both say they represent the same vector, that's the mathematical way to talk about it. So what we do is we say, and we'll say this later, I do this intuitively later in the notes, we say two directed line segments are related if they have the same length and the same direction. So if you write down an arrow and I write down an arrow on a plane, and they're both the same length and the same direction, then we'll say they represent the same vector. Not that they are the same vector, but they represent the same vector. Okay? And so vectors are actually equivalence classes. There are millions and billions of directed line segments, all with the same direction and length in the same class. So an equivalence relation like this 1, 2, 3 on the screen makes equivalence classes. Now, I'll give you a simpler idea. If you guys don't wear watches anymore, I don't suppose, because you haven't figured that out yet, but we used to wear watches. And watches told us the time. We didn't have to have the batteries working to know what time it was, okay? And we might have to wind the watch, but anyway, I will get off of that. The point is that watches used to have numbers on them, 1 through 12, okay? Now digital watches, I know they don't have that anymore, but they used to have those. But if somebody said come at 2, it wasn't clear necessarily what they meant unless you took it to mean the next time it was 2, because 2 in the clock in your watch means 2 different times, because 2 in the morning and 2 in the afternoon, or 2 in the early morning and 2 in the afternoon are different times, but the clock doesn't know the difference. And it turns out that there's a relation there, that the clock numbers 1 through 12, you take those numbers and you say 2 numbers are the same time if when you take and divide each of them, they have the same remainder. So 25 o'clock is the same as 13 o'clock, which is the same as 1 o'clock, because if you divide by 12, you get the same remainder every time. And so clocks are equivalence classes. The number you put on the face is you name the equivalence class, like 2 o'clock. But that stands for 2 and 14 and 26, and it stands for yesterday at a certain time and so on, okay? There's an infinite number of things on that clock face that the time stands for. It depends on what day, week, month, year we're talking about. So, you may have been born at 2 o'clock on some days 20 years ago, and maybe you know that, but that certainly is, if they had the same wristwatch, it'd show the same time, but it's sure different because it's 20 years later. Well, enough of that. Anyway, all over the place in the world are equivalence classes. What we do is we don't worry about that. We name them something, and then if we need to take 2/4 instead of 3/6, we don't worry about it. We think it's the same fraction. Well, it's in the same equivalence class, actually. It's 2 different names for the same thing. And that's what we're trying to set up here. So that's what that's about. And so what this lemma here, I'm going to get off of this and go further because this is not so important to us. You're not going to be tested over this very thing here because it's kind of complicated. But this is basically saying that if you do have an equivalence relation, if you have all these 3 things, then that takes the original set S and cuts it up into pieces, and it's like wastebaskets. And each number or thing is in some wastebasket, and everything in the same wastebasket is related, and nobody is in 2 wastebaskets. So this first thing says for each thing in S, it's in a class that you could use its name, but it's in a class. Like 1/2 is in the class 1/2. 2/4 is actually in the class 1/2 because we usually name the class 1/2. We sometimes say 2/4, but that's just because we mess it up. This says if X is in the same class, or if X is related to Y, then they're in the same wastebasket. And this one says that you don't have anything in 2 wastebaskets. If you have something in both wastebaskets, the whole wastebaskets are equal. Okay? So that's just saying you take the whole thing, if you take all these directed line segments and we put them into wastebaskets, each wastebasket is named something that has the same length and direction. And you can do that geometrically, and that's what I then do a little bit later. I'll give you a headache here. By going further here, when we get up to someplace beyond this first stuff here, when we get up here to 23, I try to explain stuff to you as if we're trying to build all of these equivalence relations and stuff just from saying, I know what length and direction is, and so I know what vectors are, and then we're going to try to tell you just with that information, how do you add them, how do you change their length, how do you change their direction, and it's really kind of tough to do. So I spend 3 or 4 pages, or maybe 8 or 9 pages, trying to define that. I'm sorry I shake this up a little bit. It's a lot more steady on my screen than it is on yours. I'm looking at 2 different screens, and I see I'm giving you guys probably migraines. But anyway, this stuff here, starting on page 23, is meant to just say, okay, how could we try to discover this? Now, what you're going to find out when you read it through, it's difficult and it's tedious, and we're not going to use it anyway. But what you're kind of putting down is what you'd like to come out. How do you want to add 2 arrows so it comes out right? And that's what it's about, okay? Now, I'm not going to talk about that anymore right now. I'm going to go back, so you might close your eyes a second until I get back to the beginning, to talk about this, some more abstract. I'll get by just a second, it'll get better. I decided this is better than trying to do it live for you with the thing looking on the paper. If you disagree, you can tell me. Okay. Next thing to talk about is what's a binary operation. And I think I got to go back just a little bit here. Okay. So on the screen now, I hope, in the middle of the screen is first the exposition. What is a binary operation? Well, that's a fancy 2 words for binary is 2, and it has to do with putting 2 things together. And there's all kinds of ways in math we put 2 things together. And by the way, all this is kind of a review in general, but we're going to get real specific pretty soon. When you add 2 numbers together, you're using a binary operation. When you multiply 2 numbers together, you're using a binary operation. Okay? Now, subtraction and division are not binary operations. They are built out off of addition and multiplication. Now, if we take a set of numbers like the counting numbers, which would be 0, 1, 2, 3, 4, 5, 6, 7, and so on, you can define how to add 2 of them together. You can define how to multiply 2 of them together. Okay, and you know how to do that. Now, it may come as a surprise to you, if you haven't heard me spout about this before, that you can't subtract 2 whole numbers. You can only take differences, because we want what's called a closed system. If you're trying to combine things, you want to get something that's already there, or you want to create something new and put it in the same set. When you add 2 whole numbers, you will get a whole number. When you multiply 2 whole numbers, you'll get a whole number. But if you try to take away more than you got, you don't get a whole number answer. So if you've got 4 pieces of pizza and 6 children, you got a problem. Okay? If you got 6 children and 10 pieces of pizza, you got a different problem, but everybody eats. Okay? So in one level of elementary school, you learn you can take 6 from 10, but you cannot take 10 from 6. The next year you learn, well, if you take 10 from 6, you get a -4. And that's never explained correctly, because most elementary school teachers do not know what I'm going to tell you in the future here. The point is that integers are created from counting numbers by a process that uses equivalence classes. And integers are actually equivalence classes of pairs of whole numbers. And you may have never heard that before. I don't know. I've spouted about this in the 243, but maybe you forgot. Now, if we go to a different system, if I go to integers as if we know what integers are, that's +2 and -4 and so on. And by the way, we don't get a negative number by sticking a minus on a positive number. We'll talk about that later. But anyway, if I have integers, so I have +5 and I have -2, and I believe I understand those numbers. What we do to make a rational number, to make a fraction, when you see it, think of a fraction. If I say 1/2, I think you see a picture of 2 numbers. Now what you ought to see is a picture of +1 and +2, not 1 and 2. When you drop the signs off of the numbers, you're actually changing the numbers, but we'll worry about that later too. Anyway, but I presume you will agree to me, I could take -1 and put it over -2 and get the number 1/2, just because we know about fractions. Okay? Now, so when you see a rational number, you see a pair of numbers. You don't see them written as a pair. You see one written with a line over the other, but that's two numbers. And I presume you'll agree with me that 1/2 is different than 2/1. 2/3 is different than 3/2. So the order is a difference. So you have, if I have 2/3, I have a 2 and I have a 3. Really, I should have a +2 and a +3. But anyway, I have a 2 and a 3, and that's two numbers, and the order is important. And so we can visualize rational numbers as ordered pairs. It turns out that if I have two ordered pairs, A, B, and CD, A, B, and CD, they are related when A times D is B times C. Now, to get ahead of ourselves, if we write the fraction as A over B and C over D, you know that already. Because to show two fractions are equal, you cross multiply. And if I have A over B and C over D, I multiply A times D, the top times the bottom. You know that's numerator and denominator and so on. AD and BC, and if they're equal, you say they're the same fraction. Well, we only get the dividing sign on it later. You really should be starting out with ordered pairs. So what I'm trying to tell you is rational numbers are equivalence classes of ordered pairs. What's new maybe, because you know that because that's the way we write them. You just don't write them as ordered pairs. Whole numbers make integers, and integers are equivalence classes of whole numbers. And the relationship there is that if I have two whole numbers paired, AB, and two whole numbers paired, CD, they're related when the first plus the fourth is the second plus the third, instead of the rational thing, which is the first times the fourth is the second times the third. Now, I'm trying to give you this as background. This is not part of our course exactly, but I'm trying to show you how much equivalence classes are everywhere. They're in all of our number systems. Okay, you just may not know that before. But when you try to prove things, you got to know what they really are, not just what we talk about out in the public. And so I'm trying to bring up, we need to define things when we add things together. Like when we multiply matrices together, we now know what the definition is. When we add vectors, we got to know how to do that. When we add functions, we got to know to do that. Those are all binary operations. So what's on the screen are those words binary operation, and then I try to explain what it is, and it gets worse, okay? So a binary operation is a function, and I use B for binary here. It's a function. That's interesting. Okay, that corrected itself. Okay. In this domain, and maybe I shouldn't move this over here. Maybe does that mess you up, or is that okay? I mean, should I be moving the cursor? I can do this without the cursor, but all right. A function, the domain is a set of ordered pairs. So what you're doing is taking two numbers, because we're usually doing this with number systems. Take two numbers, and I'm going to put them together in some way and get something that's in the same set that I started with. If you do that, that's called a binary operation. Okay, so addition's a binary operation and multiplication's a binary operation for most systems. Now, and I say here, this correctly would be B of the ordered pair. You see, the parentheses, when you do f of x, you do f of, and then you do the x part. Well, if the x now is an ordered pair itself, you get two ordered pairs. I'm sorry, you get two sets of parentheses. What people usually do is just drop off one. And they know, they're supposed to know it's B of this, but you write without the outside parentheses, so you'll see this down here. That's an abuse of notation, okay? And you're going to find out that as we get more into things, because A and B won't always be numbers, they might be things that don't look like numbers at all. You've got to get very careful about how you say stuff. And if you want to pass. Anyway, we have laws that we attach to binary operations. And you know these laws, you just never maybe seen them written this way before. This says, I call the operation commutative if I operate in the order A and B. If I put things together A, then B, I get the same answer if I put together B, then A. Okay? Now, if you've already read here, you know down below here a little bit, I say, well, what we really do is we write them this way most of the time. And if I write it this way, this should look familiar to you. This is commutative. If instead of writing it with the B's, I put a dot in between. Now, by the way, this is not a dot product, okay? In section 3 of chapter 12, we do dot products. This is not a dot product. This is multiplication. One of the problems with symbols is we don't have enough symbols to say all the different things we want to say. So that's a problem. And you have to know what system you're in to know what the symbols mean. In this case, it means multiply. It might mean add. It's just a way of saying put A first, then B, and B first, then A. I haven't said it's multiplication necessarily. When you see that, you'll think it's multiplication. But this could be addition. Depends on how I define it. Okay? Associative says if I combine A and B first and then C, that's the same as if I combine B and C in that order and did A, you see? Well, you know that's true for adding. You can add 3 numbers in any order. That's commutative and associative both, because you can switch them around. Now, what's the third one? The third one's called an identity. An identity is something that leaves things alone. For adding numbers, an identity is 0. When you add 0 to something, you leave it alone. When you multiply, an identity is 1 in our number systems. Okay? If we're talking about matrices, to talk about something we're going to define later, there's an identity matrix. The identity matrix in addition is a bunch of zeros in an array. The identity matrix in a multiplication turns out to have some ones in it. We'll talk about that later. Now, an inverse of something, you know about inverses, but an inverse is a personal thing. So first of all, to have an inverse, you have to have an identity. Because what you do, if you take a thing and you want to say what is its inverse, it's a thing that when you put them together, you get the identity. So for example, if I'm in integers, +3 and -3 are inverses under addition, because when I add them together, I get the identity 0. Okay? So we say -3 is the additive inverse of +3. And we're going to find out that numbers can only have one inverse at most. But if I go back to whole numbers, if we live in the world 1, 2, 3, 4, okay, then none of those numbers have an additive inverse. If you try to solve the problem 4 plus x equals 0, and you're limited to whole numbers, like pieces of pizza, okay, there is no thing to add the 4 to get to 0, because nobody eats. You have to have integers, you have to have negative pieces of pizza to represent being eaten, okay? So in the whole numbers, you don't have additive inverses. There is no -3. To have a -3 plus 3, or 3 plus something would have to be 0, and there is no such thing. So you can write the symbol down with a minus in front of the 3, but it has no meaning whatever. So when you've been writing that all your life, you've been writing things that don't make any sense whatever. Anyway, once you define these things, you can start proving things. It turns out, and these things are kind of so simple, they're hard. How do I prove that if I have an identity, how do I prove I have something that leaves you alone, all right, if you're a number? How do I prove there's only one? Well, the way you do that is you assume there's 2. So I assume I have an identity. That means when I combine, and I'm using this way to do it right now with this B, we'll get away from that. When I combine E and A together, I get A. When I combine A and E together, I get A. So that's saying when I use A on either side, that's like when I add 3 plus 0 or add 0 plus 3, I get the same answer, 3. And suppose the same thing is true for B and for D, okay? Then what happens when you put E and D together? Well, E is an identity, so it leaves D alone, and you get D. But D is an identity, it leaves E alone, so you get E. So D equals E.
Dr. Brady.
Yes, sir.
Does someone need to be let in? I think Jordan.
Oh, Jordan does, yes. Let me get to Jordan. Thank you. Jordan, sorry I didn't see you.
If you haven't joined the group me, I'd recommend doing it so you can get in easier.
And Jordan, I already took attendance, so if later I don't give you enough points, you might remember that you were here today.
Got it. Thank you.
Okay. I can take another snapshot. Maybe I can do that later, but or maybe I can do it right now. I hope I have less trouble than I did a minute ago. So if I want to do a window, it says here, choose a window. Wait just a second. So I suppose I took another snapshot. So now, Jordan, you're in the class officially and all that. Okay. So, all right, you guys need to read these pages pretty thoroughly. I'm not going to spend, I mean, I can spend 6 weeks on just these pages that I've given you. And so what happens is you carefully go through, as I say, this particular argument is so easy, it's hard. If you had to do this yourself, you may not be able to figure it out because you way overwrite it. It turns out to be easy. Now, if we have number 2, if I have an identity and I have an object that has an inverse, then no other number can be an inverse. An inverse is unique. And we need to do, once we know that, it's true for every system. Well, here's the proof. Little proof that shows you they're unique. And you can look at that. And then I do some examples here, and I've already talked about this a little while ago. The only whole number that has an additive inverse, meaning you add something to 0 to get 0, there is an answer, it's 0. So 0 is minus 0 because this is a symbol we mean for inverse. When we have an inverse, we put a minus in front of it. That's what I say right here. Okay? So when I want to talk about an inverse, I put a minus in front of it, in the middle. Okay? Don't care what you did in the past. You were probably wrong. Now, I do it wrong too because I know better, but I sometimes do it. Anyway, this says the additive inverse of 0 is 0. And that means 0 plus 0 is 0. In the whole numbers, that's the only number that has such a property. This has nothing in the whole numbers. There is no such thing. The inverse of 3 does not exist because if you put 3 up here, 3 plus what is 0? There is no such thing. So all whole numbers are for counting, and they're very useful for counting, but they're not useful for doing banking. Okay, at least if you write checks or if you deduct stuff, they're not good. You're not now. If you're a right kind of banker, you're never supposed to take out more than you got in, and therefore you could use the differences instead of subtraction. But if you don't have any money and you write big checks, you have entered the integer system, and for the bank, that's a penalty. Okay, so what you have to know sometimes if you have an arithmetic problem is which system am I in, because the answers are different. For example, if you multiply whole numbers, 1 has an inverse, because 1 times 1 is 1. We usually write inverses with a little superscript. But this has a meaning, but this does not. This means a number to multiply to 3 to get 1, and there is no such thing. So whole numbers are good for adding and multiplying, but not good for inverses of either adding or multiplying. That's one example. But just quick, because we're going to run out of time if I spend too much of this. Integers are different because they have inverses of addition, but they don't have inverses of multiplication. But integers were developed, they came in the 16th century, not before that. They were invented to do banking, to do trading, okay? And so that involved adding and subtracting, but not multiplying. So integers were developed to solve a problem they had, but they didn't solve the whole problem because they didn't have multiplicative inverses. When you get to rational numbers are defined to have both additive inverses and multiplicative inverses. And one point I want to make here is these are separate systems. When we get to the real numbers, we put them all in the same system, but they're actually separate systems with separate rules. And what you need to know when you're working on something is which system I'm in, so I use which rules. And that's what they never taught you in grade school or high school. Now, generally, so all of a sudden we're going to get a lot more abstract. I've been talking about systems of numbers. This next thing is what a group is. Now, what happened in the 20th century, and I'm going to have to spend more time on this, telling you, Friday, and we're not going to, I'm hoping you try to read all of this, and we're not going to be able to go through all of it, but we're going to be coming back to it throughout the semester. So I'm going to soon be going to chapter 12 without covering all of this stuff, but we're going to be taking pieces of it, and I may remind you about it. Go back and read this later, okay? Because we could spend a month. This is actually what's called modern algebra. We have a whole year of course on it. So I'm trying to give you enough of it to give us ways to do things easily later, so we don't have to keep doing the same thing over again. Okay? If you stay with me, you'll profit. Okay? If you think I'm crazy, well, drop the class and maybe we can have everybody come to the same class at the same time in class. I'm joking now, but hope nobody drops. Anyway, a group is an abstract thing. It's a set, and it has an operation, one operation, and in that operation you have an identity, okay, and that's number one there, and each element has an inverse, okay, and it's only defined on the left for the identity and only defined on the left for the inverse. Earlier we talked about things on both sides, but for a group, it's a structure that you have on sets. And what happened in the 20th century is mathematicians found out that lots of different things have the same properties. And so they begin to classify things abstractly. And it turns out that matrices and functions and numbers and stuff all have a lot of the same properties. So we classify the properties. What we say is the real numbers are a group under addition. The real numbers are a group under multiplication. That's not quite true, but it's 20 after. Anyway, this is an abstract object with one operation, and there are properties, and I proved properties here for several pages about what a group is. Then we throw in a second operation, that's called a ring, okay? And that's you put in addition and multiplication together with a set. And then later we put in more properties and we get a field. The real numbers you guys have learned about is called a field, okay? And that's going to come quickly. It hasn't come to you yet, but now it'll be there. A field is like the real number system or the complex number system or vectors. Vectors turn out to be fields, okay? And so all this stuff up to about page 19 is, and by the way, you have ordered fields, and that has to do with when you want to put order on things. The real numbers have an ordering system as well. We know what's bigger and what's smaller, okay? And so for the first time, you call things positive. And I define here what you mean by positive. So what I'm doing is defining all of the mathematical things you've ever had before. And I'm giving you that in 20 pages. It's the 12 years of math you had in high school. These are all the rules and all the properties that you had before. And I'm trying to put them down so there's a place we can go look for them when we get into something new. And in the end, it makes it much easier. But it's like climbing a mountain. You've got to get in shape first. And so what I'm trying to do here is the hard stuff, is doing the calisthenics here, trying to put down the beginning stuff so that when we later want to use it, it'll flow freely. Now, it's 21 after, and some of you may have to go. I'm going to turn off the recording now, if I can find the place. Pause recording, stop.